In this final lesson of our class, we're going to spend a little bit of time talking about taking a sequence and adding its terms together. And in particular, using summation notation. So you might have seen summation notation before, or this might be your first time seeing it. I'm going to assume it's your first time seeing it. So the first thing I want to talk to you about is this symbol here. Okay? So this is the summation symbol, and we use the Greek letter sigma. So this is uppercase sigma. And sigma is the notation that is used to indicate addition. The history of this is something that we can talk about. As with all history of mathematical notations, it's really interesting, but we're not going to go into it right now. So what does this mean? What we see in the symbol sigma is kind of the guide of what to do. So you see that we have the summation, right? So again, that's Greek letter sigma stands for summation, and then says add everything up from k equal to 1 to k equals to n. So this summation is indexed on k. And then it says what we're adding together is a sub k. So what we're doing here is we're taking from k equal to 1, which is a sub 1, all the way to k equals to n. Notice, and I just want to sort of point this out, almost more for much later in your mathematical journey than for now, but I want you to notice that this is a finite sum. So there is a beginning, which is the first term, and there's the end, which is the nth term. So we're adding together the first n terms of this sequence. It is possible to have an infinite sum. That's called an infinite series, and we're going to mention them very, very, very briefly, but we're not going to talk about it a whole lot. When we have infinite series, things get really, really much more interesting very quickly, and you need some pretty sophisticated machinery in order to be able to work with them. But we will say a few things. So let's try this. We're going to try a couple examples. So for the first example, we'll look at this sum. So once again, we are indexing the sum on k, right? So we are adding together all of the values of k starting at 9 and going to 13. So we have simply 9 plus 10 plus 11 plus 12 plus 13. Okay, so you can do this on a calculator, you can do it in your head. Let's just do it quickly together. 9 plus 10 is 19, plus 11 is 30, plus 12 is 42, plus 13 is 55. Okay, so that is the sum here. Let's try another one. So this is an example where we might want to think about the pattern rather than write out all of the terms. So here we have this sum. So notice that in this case, we're indexing on j. So we're adding up from j equal to 1 to j equal to 145. So in the previous example, we only had to write out 5 numbers and add them together. Here we're going to have like over 140 of them. So this is one of those cases where I don't think I want to write out 140 numbers. I think I want to observe what the pattern is and go from there. All right, so I'm going to write out the first few terms and see what we see. So negative 1 to the first power is negative 1. Negative 1 to the second power is positive 1. Negative 1 to the third power is negative 1. Negative 1 to the fourth power is positive 1. Negative 1 to the fifth power is negative 1. Negative 1 to the sixth power is 1 again. So what we notice is that we're starting off on an odd power, right? We're starting off with the first power of negative 1, and it actually reduces with the even power that comes directly after it. So starting with an odd power, the even power that comes immediately after it reduces it. So once again, I just want to point out that we got to the sixth power here. Okay, and what we see so far is that the first 6 terms, so these guys here, there's 3 couples, and each of them reduces off to 0. So this reduces, this reduces, this reduces. So every single odd numbered term reduces with the even term that comes right after it. So let's fast forward, and we get to negative 1 to the power 145. Well, 145 is odd, so negative 1 to the 145th power is negative 1. If we kept going, the 146th term would be positive 1, and it would have reduced with this, and we would have been back to 0. So again, the 143rd and the 144th term, those were negative 1 and 1, and those reduced off. So what we see is that negative 1 to the 145th power is without an even pair. So what that tells us is that the negative 1 to the 145th power has nothing to reduce with, and so it's going to be left behind, and the sum of this is going to be negative 1. So again, it's really important when you have a lot of numbers like this, it's really, really important not to think about, hey, should I write out all 145 of them, or is it okay? Okay, so I want to really, really, really quickly mention to you the idea of geometric series. So geometric series, this is not a topic that we cover in this class super thoroughly. In fact, this is the one time that I'm going to mention it, but I want you to be aware of it. So the idea is that rather than taking a finite sum, like we did in the examples before, this is an infinite sum. Okay, so if we go back to our previous conversations, we know that a geometric sequence is a sub 1 times r to the power n minus 1. Okay, and to turn it into a series, we simply put on a sum. So what we'll do here is we can index along n, and we'll index from 2 to infinity. Okay, so we have, actually, you know what we'll do? We won't index from 2. We'll actually go ahead and index from 1. So just to kind of show you what this means is, we have a sub 1 times r to the 0 power plus a sub 1 times r to the first power r to the first power plus a sub 1 times r squared plus so on. So the thing that is a little bit of, I don't know, I think of this as something that really takes a second to digest and really kind of believe. You would think that if you are adding together infinitely many numbers, so you would think that the value of an infinite sum is infinite. So if you add together infinitely many numbers, you get an infinitely large number. And this is where, in my opinion, like, it's really important to kind of crack open this really crazy idea that actually that's not always true. There are many situations in which you add together infinitely many numbers and what you get is infinite, but not in all cases. So in fact, if r is greater than 1, so if the common ratio is greater than or even equal to 1, the sum is infinite. And if we want to use series language, we would say the series diverges. You can also say the series is divergent. But if r is less than 1, so like in the very, very first example, before we even called them geometric series, or sequences for that matter, we had that example where each term was the previous term divided by 3, and we went back later and we said, hey, this is just a geometric sequence where r is 1/3. So as it turns out, if r is less than 1, the sum of an infinite geometric series is actually finite. So we're going to call the sum capital S, and it's going to be a sub 1 divided by 1 minus r. So for example, if we go back to that very first example of a geometric sequence in which a sub 1 was 10 and r was 1/3, the sum, if we turned it into a sum, if we added the terms together, making it a geometric series, the sum would have been 10 divided by 1 minus 1/3, which is 10 divided by 2/3, which is actually 15. So if we add all those numbers together, even though there are infinitely many of them, we get a finite value back. Okay? So, there. Kind of a crazy idea, but one that I wanted to expose you to. To finish this lesson, I want to continue on with this notion of an infinite series, but I want to talk about the following thing. The notion of a partial sum. Okay, so say that you have a series, or so let's say we have something like this, and we're just adding together for n. Okay, so this is very obviously a divergent series. Right, let's take a look at it. So this is going to be 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5 plus so on. So every time we're adding the 4 times the number. So the terms are getting bigger one after the other, and no matter how far we go, we keep adding bigger and bigger numbers. A little bit further down your mathematical journey, you'll talk about being able to look at a series and determining whether it converges, meaning it has a finite sum, or it diverges. We're not going to worry about any of that right now, but we are going to notice that in this case, it feels pretty clear that this series diverges. So if we asked about S, the total sum, so the sum of all of these is infinite. Okay, so if we add up all infinite ones of these numbers, clearly the sum is infinite. But we don't have to look at the whole sum. We can look at partial sums. So S sub 1, well, that's just the first term. Right? S sub 2 is the sum of the first 2 terms. So that's going to be, let's write it out in words, sum of first 2 terms. So that's going to be 4 plus 8, which is 12. S sub 2 being the sum of the first 2 terms, S sub 3 is the sum of the first 3 terms, which is going to be 4 plus 8 plus 12, which is 24. Okay? And then S sub 4, I'm not going to write it out this time, but this is the sum of the first 4 terms. So that's going to be 4 plus 8 plus 12 plus 16. So that's going to be 40. So I will only say this. Every infinite series has a sequence of partial sums. And later on in your mathematical career, this is kind of a second semester calculus sort of conversation, you'll talk about how do you look at a series, what are some tools for looking at a series and determining whether it converges, meaning determining whether the sum of all of the terms is infinite or finite. So bigger conversation down the road, but for now, I just want us to be aware of the term partial sum and of the fact that every infinite sum or infinite series has a sequence of partial sums. That's our last lesson. Thank you for watching.